All right, our next speaker is Han, who is going to talk about entrainment of cold stream, origin of excess star formation rate at cosmic rim.
Hello, everyone. I'm Han. I'm postdoc at the Hebrew University of Jerusalem and working with Nia and Avishai on the entrainment of cold streams. And so Sebastian showed us great observations results on the cosmic webs and the filaments, and I'm hoping that I can convince you how we can relate that to the origin of the star formation rate at the cosmic noon. Right. Okay, so shown here is the specific star formation rate of a 10 watt 10 solar mass galaxy. So for a dark matter halo, this is about 10 watt 12 solar mass halos. And it's showing this as a function of redshift. So shown with the black dashed line is a specific accretion rate of the dark matter halos from the N-MODI simulations. So you can think of it as a baryon, like the total baryon accretions according to the N-MODI simulations. Shown on the blue and the green line are the measurements of the specific star formation rate from the hydrodynamic simulations, and you can see that they are slightly higher than what is predicted with the dark matter from the dark matter halos. And then on the left plot with the gray line, and on the right plot with the red lines are the measured specific star formation rate. Again, at this stellar mass of 10 by 10 and as a function of redshift. Depending on the results, then they are either very high or slightly higher than the accretion rate of the dark matter halos. But regardless of the results, the main point is, the measured star formation rate is larger than the total accretion rate of the baryons according to the dark matter simulations. So to understand where this difference comes from, I'll take you back to the baryon cycles of these galaxies. So the IGM, the intergalactic medium, is where the outside the very radius of the dark matter halo. So this is where the cosmological, you can get the cosmological accretion rate of these gas. Inside the galaxy in the ISM is where you measure this star formation rate, which is approximately on the order of the cold gas accretion rate. And as I have shown, this is larger than the cosmological accretion rate. So the key question that I would like to address is, what happens to this infalling gas from the IGM to the ISM within the circumgalactic medium in between. And the question is, so one of the proposed mechanism, or one of the additional source of the cold gas accretion is the recycling. So some of the hot gas originally in the ISM can get pushed out because of the feedbacks and the winds, and then they can cool back down and recreate it back to the galaxy. So that's the recycling of gas. And so another question is, what is the mechanism of this recycling? So to get a little bit more details into so this is where the cold gas will come from. So they are from the IGM. I'm interested in the 10 Mach 4 solar mass galaxy at redshift of 2. I guess no longer high redshift anymore, but okay, medium redshift, I guess. So these are usually the high mass, reside in the high mass dark matter halos. So they reside in the cosmic node with the multiple filaments feeding them. So shown here. Oops. Yeah. So this is and so within because of that, the dark matter halos are magnified by the dark matter filaments, and so the gas will also come from the cold streams in these dark matter filaments. These halos are above have a high enough temperature, and so the cooling times in these halos is long enough that they can maintain a hot CGM, and so they will have an accretion shocks around here. So this is shown in there. Shown here is a result from the simulations where you can see an accretion shock, and then you can see cold streams going into these galaxies. Accretion shock is, you can think of it as the outermost boundary of the hot halo gas, so analogous to the dark matter splashback radius. So if you want to know about the relation between those two, you can check out my earlier paper. But going back to the gas, if you zoom into the inner CGMs, in the simulations, you can see these like cold clumpy gas, so you can see the three filament tree streams, but most of the gas in them are cold and clumpy, and this is also the similar things that we find in the observation as well. So whatever happens in the middle, the instabilities, fragmentation, etc., that will lead to that will changes from the cold streams to these like cold clumpy gas in the inner CGM. So to study what happens to the gas within the CGM, we will use the idealized simulations. So in most of the cosmological simulations, most of the zoom in regions are within the inner regions where the density is highest, but there's and the refinement of around the stream is relatively smaller usually. And so we'll use idealized simulations to study what happens to these cold gas streams. So first, a summary of some of the properties of these cold streams. So that these can streams can cool efficiently, and so they'll have about 10 bar full Kelvin from the cooling curve. And then the gas you usually have a very temperature of about 10 bar 6 Kelvin because they don't cool effectively. And so if you assume pressure equilibrium, you can measure one of the dimensionless parameter that is important for this problem, which is the density contrast, about a factor of 100. Then you also assume that these gas streams are flowing in because of the gravitational potential of the halo, and so the velocity will be about the Fourier velocity. And the background gas, the sound speed, you can estimate sound speed from the Fourier temperature, so both of them are from the Fourier relation. So the Mach number of the stream relative to the halo is on the order of 1. That means that as the streams goes in against the stationary hot halo gas, they will experience the Kelvin-Helmholtz instability because of the shearing between the two. So one of the time scale that is important for the Kelvin-Helmholtz instability is the time scale for the instability developed, which is on the order of sound crossing time across the stream. So from the cosmological accretion rate, you can estimate the m dot, and then from the flux, then you can estimate the radius of the stream as well. And so this is important because you need to know how long the instability has to grow before the stream can reach the galaxy in the center. So ratio of the sound crossing time to the Fourier crossing time. So based on these parameters, we look into the idealized simulations where we just put in a cylindrical gas streams that is flowing with standing velocity against the background hot halo gas, and you can see the Kelvin-Helmholtz instability develops on the left on its left panel, and you can see that the stream will get slowly disrupted over time because of the shearing and the mixing. Some other additional effects that can affect, for example, the self-gravity of the streams can lead to the clumping of the gas. But what is important to the process that I want to discuss is mainly the cooling. When the Kelvin-Helmholtz instability mixes the cold gas with the hot gas in the background, the mixed gas will be warm, which can rapidly cool. And so what is important is this time scale ratio of the time scale of the cooling time in mixing region versus the stream disruption time. And so if this ratio is less than 1, that means that the gas in the mixing region can cool rapidly before it gets disrupted, and so the background gas will condense onto the streams, and so the stream will remain dense. So this is shown in the result from the right hand panel. So your left hand is a Kelvin-Helmholtz instability dominates, and so you will see that the stream get disrupted, but on the right hand you can see cold dense streams remaining. But if this cooling is not effective, then the result will be the same as the no cooling as seen on the right. But again, this is a result from the idealized simulations where you have cylindrical streams embedded in the plane background. So we would like to know what happens to the what happens when you put this into a halo potential. So some of the key parameters that I would like to discuss is the entrainment time scale. So you can calculate how fast the cold gas mass is growing by this entrainment time scale, and this is proportional to the cooling time and the sun crossing time to some powers. So what does halo potential do? So it will cause the stream to accelerate. So in the previous case, when you have no halo potential, the stream that is flowing mixes with the stationary background, and so because of the conservation of momentum, that you will slow down over time. But because of the gravitational potential, the stream will get accelerated, so this will counteract the deceleration. Second thing, because of the halo potential, you have some density profiles in the halo. That means that to maintain the pressure equilibrium, the density in the stream will also grow as well. So that means that the cooling time is proportional to 1 over the density. So you have a faster cooling as you go inside the halo, and that means you also have a faster entrainment. The second thing that will happen is the third thing that will happen is the stream will get narrower. So if the density is increasing, to keep the flux constant, you need to have a narrower streams. That means that the sun crossing time across the stream will be shorter. Again, leads to faster entrainment. So you can model these as a function of a halo radius to some power. In the previous work, we assumed beta is 2 for the conic stream, but for that constant. But if you assume a hydrostatic CGM within the NF through halo, which is a realistic scenario, then you have a varying beta somewhere between 1 and 3. The exact density profiles and the stream radius are shown here, going from a 0.1 Fourier radius to 1.1 Fourier radius. So the stream will come from the 1.1 to go into the 0.1. So along with this analytic model, we also run a few numerical simulations to test this model. So we have a simulation box that is going from a 1.1 Fourier radius to 0.1 Fourier radius, and so that we put a spherical NF through potential outside the center is outside the box, but we are encompassing the regions of the CGM essentially. And the CGM is assumed to be normally supported, so it is hydrostatic with the hydrostatic equilibrium with the halo potential. And we make sure that we have the refinement so that the stream is always resolved with more than 20 cells at all radii. And so across the diameter there is at least 40 cells, but depending on the regions, this refinement will be slightly different, but it's at least 40 cells. Okay, so one of the main results from our simulations and the predictions from the model can be summarized in this plot. Too many lines, so a bit complicated, but I will slowly explain this. Okay, so the y-axis is showing the radial mass flux of cold gas normalized by the radial mass flux at 1.1 R area. So where we put in the gas at the red line shows the mass flux of the original stream gas, which is about 1. So this is mass conservation essentially. But ignore the different color lines for now. Let's look at all the color lines, and as you can see, they all grow from 1 to somewhere between 2 to 4. So this means that the radial mass flux of the cold gas is growing as you go into inner halos. So this implies that in addition to the radial flow, there is an additional mass flux that's coming from the perpendicular to the stream axis, and this is basically explained by this entrainment of the cooling. So as the streams goes in, they mixes with the background and the hot gas with the cold gas, and then this gas cools down and joins the streams, and so the cold gas mass flux grows over time. And you can get a factor of somewhere between 2 to 4, or at least in most cases, it's larger than 1. Now I'll go into a little bit of details of the different lines, but I won't explain every line, but there are a few trends that you can recognize. So if you increase the number density, then yeah, you increase the density, and so you have faster cooling and a faster entrainment, etc. And so you can summarize this model prediction. So shown in the straight lines are the model predictions, and the dashed lines are the simulations, and they are in agreement with each other. So this is a summary of the model predictions. So they are assuming that the temperature of the filaments is about 10 Kelvin, and the temperature of the background is the variable temperature of the halo. And you can measure what is the entrainment rate, which again somewhere between a factor of 2 to 4. The main trend is with a redshift, so if you go to higher redshift, you have a larger density and a faster entrainment. However, I would like to mention a bit about at what halo mass range and the redshift range is our model is valid. So the assumption of our model is that the filament can cool due to 10⁻⁴ Kelvin, and this is true for the 10⁻⁴ solar mass, which have variable temperature of 10⁻⁵. So they can cool rapidly to 10⁻⁴ Kelvin. And then CGM maintains at the variable temperature. But if you decrease the halo mass, you will decrease the variable temperature, and then that will take you to regions where it can cool effectively. So I'll skip a few slides, but the net result is something like this. And so there you have a partially hot CGM, where the inner region is cold, outer region is hot. That means that the cold stream can only entrain for some parts of the regions, and so it will have partial entrainments and stop somewhere in the center. But if you increase the halo mass, the opposite thing happens. That is, the filament temperature will grow as a function of halo mass and a redshift, and what you get is something like this. So there you have a cold streams, but you also have a hot filament. So not all filamentary gases are cold, so that means that the initial cold mass that you have is smaller than the cosmological accretion rate. So to summarize everything, at high mass and the redshift, the filaments are usually hot, and so shown in the color bar is the ratio of the cold gas accreted onto the galaxy. So the approximation of a specific star formation rate divided by the cosmological accretion rate at the variable radius. Now, if you are larger than 1, there's an entrainment. If you are smaller than 1, there's hot filament. The high mass and redshift, the filaments are hot, but at low mass or redshift, there's no CGM, so there will not be entrainment, so it is at 1. And somewhere in the middle is where you can see the entrainment. And also there's a slight trend with the redshift because, as I have shown earlier, if you go to lower redshift, the density decreases, the cooling time goes down, and so there will be less entrainments. I'm going to skip a few slides just to mention. We can use that to predict the star formation rates, which do decently well in comparison to the observations at the different halo mass and redshift. So I will just summarize this quickly. The cold gas entrainment, cold gas accretion onto the galaxy can be boosted from the cosmological accretion rate by a factor of 2 to 4 because of the cooling of the CGM gas onto the cold streams. And this can bring gas from the hot CGM back into the galaxies and provide a potential channel of the recycling. And that can explain the higher star formation rate than the accretion rate that you measure. I also mentioned that we can also explain some of the observed line alpha emissions, but which I didn't talk about in the talk. But you can talk to me for more details. Thank you.
We have time for one question, actually. And can the next speaker come up and start to set up?
It's a fascinating study. So I was trying to understand why in the regions below halo mass is 10 to the 11, the mechanism does not really work, because you mentioned the cooling, but you were very fast. So can you please explain again? So yeah, in the gray region, why is it not working?
Yeah, so for the entrainment to work, you need to have a cold filament and a hot CGM. Right? But at these low halo mass, there is no more hot CGM because the cooling is very efficient. And so because there's no hot CGM, there's no hot gas to entrain from, and so there's the model, there's not really a hot entrainment there anymore.
Do you need HDMI? Yeah. Yeah.
It could be if there's sorry. So the question was that at the low halo mass, why does the model doesn't work, or why is there no entrainment? The answer is that at the low halo mass, the CGM cannot maintain its Fourier temperature because the cooling time is very fast. At the Fourier temperature is about 4 Kelvin. And so the cooling time is very fast. That means that it cannot maintain the Fourier temperature, and so it will quickly cool down.
Okay, we actually don't have any more time, so let's